Okay, let's talk about acids and what that means. So, we had talked before about the idea of acids in the movies and how you pour acid on something and it eats it away, and it's, acid sounds like, oh, scary, scary, scary. And while there are a few acids that are quite strong, there are usually acids are quite innocuous. In other words, that means they don't really actually do a lot of things that are spectacular like in the movies. And we're going to see that very shortly. So if we look at all the sort of different possible types of acids, which we will, we'll start to see that acids are all around us. They're very common, and we find them everywhere. All right, so let's look at some acids. I'll give you some common acids that you may have heard of, okay? So acetic acid. We'll see if we can find something familiar about them. Acetic acid. Let's see. Hydrochloric acid. You might have heard of that from the movies, or if you've done any science experiments. Maybe you've heard of citric acid. That's the acid that makes oranges all tangy and tart. Citric acid is commonly used in candies to make candies taste kind of sour and kind of sharp, right? Hydrochloric acid, acetic acid. You may have heard of sulfuric acid. That's an acid you sometimes will see in the movies or whatnot. Maybe, if you're really smart, you've heard of something called deoxyribonucleic acid, which we call DNA, which is our genes. Our genes are made of acid. They're a kind of acid, which is weird. We don't think about that. So you can see here, we have acetic acid, by the way, I don't know if I told you, is just vinegar, right? That's what vinegar is. We put that on our French fries and we eat it. Some people use it to clean their house. Hydrochloric acid is the acid that's in your stomach that digests your food. Your body actually makes it to digest your food. So and I said citric acid, of course, is the acid that we find in citrus fruit. Citrus fruit. And of course, it's got that sharp, tangy taste. Sulfuric acid is more of an industrial acid, but you know where you find it? You'll find it in car batteries. Battery acids. And then, of course, DNA is our genes. So what I'm trying to show you here is that acids are found all over the place, and they do all kinds of interesting things. So let's see if we can figure out what an acid is. Well, I'll tell you, there's a number of different sort of ways of classifying acids. And in grade 11, you will learn the different kinds of official ways to describe them. But we're going to just try to look at them from their behavior point of view. Okay? So let's take what would happen with, let's say, something simple like HCl. Okay, HCl is a molecule. We would call that hydrogen chloride, right? That's what we would call it. But if we dissolve it in water, remember from yesterday, the little AQ stands for aqueous, which means if we take some of that and we dissolve it in water, the water can pull apart those ions, the H and the chlorine, the hydrogen and chlorine ions, and it can dissolve them. And once you do that, this particular thing becomes an acid. Now, water can also dissolve salt, right? You don't have to write this down, but remember NaCl. But it does not become an acid. Obviously, when we put salt in our water to make pasta, it's not an acid. So why is one an acid and not the other? And we're going to see right now how that works. So let me erase this. So let's see what happens if we take this HCl and we dissolve it in water. Remember, that's what this little guy right here means. He means we're going to dissolve it in water. Okay. So let's imagine then that this hydrochloric acid is inside this very large cup. And we'll put this water here like this. Okay? I've never seen waves in a cup before, but if you don't make the waves, it doesn't look like water. So I guess we have to do the waves. All right. So remember from yesterday, what happens is because water is a polar molecule and it has sort of a positive and negative side, because the electrons are not evenly spread out, they're being hogged by the oxygen side of the water, then it can pull on ions, those sides of the water. So when you put the hydrogen in the water, here's what happens. The H plus gets pulled away from the Cl minus. But notice how the electrons stay transferred, right? Hydrogen's electron was given to chlorine, and it stays with chlorine. So this is a chlorine ion. It's not atoms that are separated, it's the ions. And so the water molecules sort of gather around in this manner, because the H side of the water molecule, remember how it's a little bit bent? And the H side of it is the positive side of the, what we call the dipole, the two poles, the positive and negative poles. And those poles are there because oxygen is hogging the electrons. So maybe I can put a little green here, we can put the little charges. This is the positive side of the water molecule. Remember, that's what that little sigma means. And it's attracted to this negative chlorine. Okay, now likewise, what happens over here on the other side is that the water molecules are also going to be attracted to the plus of the hydrogen, but they're going to attract in the opposite way. It's the O side that will sort of line up here. O side because the O is the sort of negative side of the water molecule, right? It has this polar nature. And that's incredibly important for just about everything that happens inside water. And it allows for a lot of chemistry to happen. Now, something very cool happens. Not much happens over here. The chlorine is just sort of happily balancing itself there, right? But this part of the water is going to do something kind of unique. Okay? I call it the water dance because it's kind of like a dance where you exchange partners. So let's examine this in more detail. Let's draw a close-up picture of a typical water molecule, right? Like this. It's sharing its electrons with these two hydrogens, but it has these other electrons here that are not being shared, right? They're just kind of sitting there. Now, along comes an H that's sort of, that's being surrounded by the water molecules. You see it up here in the other picture, right? This H right up here, this red H, it's positive. So it will be attracted to negative things. And what happens is, if you notice, right here, there are two negative electrons that aren't doing anything. Now, a hydrogen might just ride over here and be attracted to the negative charge of those two electrons and sort of hang out there. In fact, it's almost like it's forming another shared bond, except here it's not sharing anything. It's coming in with nothing, no electrons. But because there's two here, it's going to hang out with those oxygen electrons and form a bond. We call this a special kind of bond. It's a coordinate covalent bond. It's when something comes along like this with no electrons, but it still is able, remember, it's still a shared pair, right? It's just that oxygen is providing them both. And so what happens is, for a moment, we get this. We get an O that has its H's And now we have this other H over here attached right there. And what we call this is H3O, but there's something special about it. Because we've added this extra positive thing to it, and no electrons came with it. That means if you start adding up all the pluses and minuses inside there, there'll be an extra plus. So this becomes an ion that has a plus charge. He's called the Hydronium Ion. Hydronium Ion. And so what this means is that when something like HCl dissolves in water, see this hydrogen here? This hydrogen can attach to the water molecules nearby and create this hydronium ion. And so any molecule that has hydrogens that are able to be released by the water, able to be pulled apart like this, see up here, they're pulled apart by the water, and we get this situation. Any molecule that can do this will produce these H pluses, right? Which will then join up with the waters to make hydronium ions, and they are acids. Anything that can do this is called an acid. Okay. Now, here's what I mean by the water dance. Let's say we have just pure water. I'm going to call this the water dance. Here's a water molecule happily doing its thing. Here's another water molecule that happens to float by. Because, of course, in the water there are many, right? Now, let's look right here. This hydrogen ion, or this hydrogen that's attached to the red water, is attached there because it's sharing a covalent bond, right here. It's sharing electrons with the oxygen. But as we saw, what if that H left its electron there, said, screw that, I don't even want that electron anymore. And it went away. It could break off of there. I'll draw it in green. So he's no longer there, but he left his negative electron behind. That's why he's a plus. And then, as we saw up here, a positive hydrogen can sort of link up to the oxygen where it has 2 electrons. So he could actually go over here and link up to there. And so what we would have is a little sort of interaction where we had a water molecule, right, that comes up towards another water molecule, and those water molecules exchange these H's in such a way, and they produce an H3O plus on this side, and then they produce something else. What's this called? Well, that's our little friend hydroxide, remember? He's basically just an OH. But if you notice, what's important here is that this hydrogen, when he left, he left his electron behind. That bond is still 2 electrons. He did not take it with him, which means that if he leaves, the OH now has more minus than positive, so it becomes this. Now, what happens then if you make these 2 things? So now you have an H3O plus, right? And here's the other H attached. And then there's an OH over here. So let's say that these 2 were made and they went off around in the water and they bumped into another one. Well, this O, right, it's bonded there, but it still has places where hydrogen can bond. So now they bump back into each other, and this H says, oh, okay, maybe I'll go back over here now. And when he does, you have the OH minus and the H3O plus. Now, guess what you make, right? You make a water molecule, a normal water molecule. In fact, what you make is two water molecules, right? So if we were to balance these equations, if we were to go up here and balance this, we would say two H2Os get together and they produce an H3O and an OH. And down here we would say an OH and an H3O produce two H2Os. So you see what's happening? The little hydrogen is bouncing around. He's trading partners. He's like, la, 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 and I'll hang out with this guy. And then he's like, whoop, and he hangs out with this guy, and he keeps jumping all around. So if we were to look at a glass of water, we wouldn't just see H2O in there. We'd see H2Os all over the place, right? We'd see them. Here they are. But we would also see some H pluses, or H3O pluses, actually, because some of these water molecules would have bumped into each other, and those little hydroniums would form. So there'd be some of those in there as well. And then there'd also be some OHs, like this, some hydroxides. And what's interesting is it's not just idly floating around. As they bump, they keep switching into each other. So this H2O right here might pop into an H3, he might turn into two of these, and then this might go over here and around and swim over and bump into that and turn back into a water, and then this. So it's like a big jumble. It's like a big complicated dance where the H's are all being passed around from one to the other. And it's a creation of what we call an equilibrium in chemistry. Okay? And what's important to notice about an equilibrium is it means that everything is still relatively balanced, except it's constantly moving. So actually what we call it is a dynamic equilibrium, as opposed to a static equilibrium. So let me show you in another way what that might mean. Let's imagine a classroom full of people. Okay? If I put the people here in the classroom, and I put boys and girls around in the class. Girls, boys, girls, okay? And we have the same number of boys and girls, and they're all just sitting there and nobody's moving. That's what we call a static equilibrium. It's equal, right? It's equilibrium because it's the same number of boys and girls, 4 and 4. But if I put all those girls and boys on the other side, or on one side, girls over here and boys over here, well, that's not really an equilibrium. It's a separation, right? I mean, it's still an equilibrium in a sense, but we now have a noticeable change. We have poles, right? That's what we have here. But imagine if they weren't just sitting in their desks. Imagine if they were free to walk around, right? If they're free to walk around, then you could have boys and girls sort of going all over the room, boys here, and this boy's walking over there, and this boy's walking over there, and there's another boy walking over here, and they're walking all around, and the girls are moving. So it's a big jumble of motion. They're still 4 and 4, but they're all jumbling around. That's what we would call a dynamic equilibrium, because everything is moving in motion, but nothing's really changing. Okay? What's important to notice with the water is that we have H2Os dancing around, and we have H3O hydroniums, and we have hydroxides dancing around in there. They're all turning into each other, and they're moving and dancing. But even though they're turning into each other, if we were to take a picture with our camera at any moment and count up how many hydroniums and how many hydroxides there were, would always be the same. There'd always be the same number, just like the same number of boys and girls here. It's not like we get more hydroniums and less. It's always equal. That's why it's an equilibrium. And so how we describe this is we say that two water molecules, and we put an arrow that looks like this. It's a double going both ways arrow. It means this can go back and forth. And then what it produces is an H3O plus and an OH minus. Right? And of course, what we should do is we should also write little AQs here to show that these are dissolved in the water. They're sort of in between the water. But it's a dance, because this H3O is not going to last long, because he's going to bump into another hydroxide somewhere, and he's going to turn back into water. Right? You know the old square dance where you swing your partner and then you go and you do-si-do around, you link arms with all the different people and you keep switching? It's like that kind of a square dance. So it's not just molecules floating. It's a constant interaction and change. But what's important is that if you look at this, it's always the same number of each, the same amount of each at any given time. And that's what water does. That's what the water dance is. It's this constant switching back and forth between these two ions and molecules. Okay. Now, because this is the same number of each, that's the key. We say that the solution is neutral. We call it neutral because it's even Steven. There's no extra hydroniums or extra hydroxides. It's pretty much the same of each, right? Because for every water that breaks up, there's another one that joins back together, and you never get any buildup of any one or the other. That's what we mean by an equilibrium. Now, let's see what happens when we put all this together. If this is what water is doing all the time, and it's in this nice balanced equilibrium where we have the same number of hydroniums and hydroxides all the time, if you put this molecule up here of HCl in there, where was it? Right here. The HCl is going to produce H ions as well, hydrogen ions, and those are going to make hydroniums as well, which means the acid will be adding extra hydroniums. So the hydronium is going to start to go up. It's going to go out of balance because we have two places now where the hydroniums are coming from. And so when we add an acid to water, when acids are dissolved in water, they release hydrogen ions, which form more hydronium ions. They link up with the waters nearby. This means there is now an excess of hydronium ions. In the solution. Okay, we've driven it out of balance. So normally water just has its own little dance, and it usually has equal amounts of both. But by adding this molecule of acid, we create more hydronium ions and we throw out that balance. And that's what acids do. Acids make more hydronium in the solution. And of course, because there's more hydronium, there's not enough hydroxides to join up with them all and make waters. So there's extra floating around. It's almost like you have a square dance where everybody starts with a partner, okay? So let's think about this. Everybody starts with a partner. Here's the partners. Here's the red dancers. Okay? And here's the green. And it doesn't matter when they start to do-si-do and swing around, right? This partner goes and links arms with them and then with them. But there's always one red and one green. There's always somebody to link arms with, right? Doesn't matter who you're with. But if you add more people without a partner, well, who are they going to link arms with? Maybe three. They could link arms with each other, I suppose, but they don't because they're both, in this case, they're both positive hydronium ions, right? They don't get together because they're positive. They repel. So these guys are the odd ones out. So while this dance is going on, these guys are left over without a partner, and we call that excess. It's extra people, right? Excess. So the acid causes an excess of hydronium ions, extra ones. So that's what acids do. They upset the delicate dance of the water to create an extra amount of hydronium ions. And those hydronium ions are able to react with other things, and that's what causes acids to be reactive. Okay, so that's the idea of what an acid does. Now let's look at how we describe them all and how we name acids. So let's look at what we call the acid nomenclature. Okay. So because you need a hydrogen ion to be popped off and join up with the water to make hydronium, you're going to notice that acids all have hydrogens in them somehow. So all acids contain hydrogens pretty much, but not all things with hydrogen can be acids. It all depends on whether the hydrogen can easily be released and let go from wherever it's bonded. And so the presence of hydrogen can be sort of a little red flag indicator that you might have an acid, but only if that hydrogen is able to be easily removed from the molecule. Some molecules hold on to them harder than others, and the water can't pull them off, right? So let's first talk about what we call the binary acids. They are made of two things. And the binary acids are usually a combination of hydrogen plus one of the halogens. Do you remember which family of elements is the halogens? It's the second last column beside the noble gases: fluorine, chlorine, bromine, iodine, astatine. And so when we join these up, we get, for instance, here's some examples. We get hydrogen and fluorine, HF. And because it's a hydrogen, we use hydro. And then it's fluorine. So what we say is, to make it sound like an acid, we say fluoric. Whoops, let me spell that right. Got flour there. Fluoric. With that little dot. Ick. We change the ending to ick. When you see an ick ending, it's a good probably you're looking at an acid. Deoxyribonucleic acid. Hydrofluoric acid. Okay? And of course, we could have hydrogen with chlorine, and we would call that hydrochloric acid. There's the ick. Oh, I should write the word acid. Okay? And one more technicality. This is important. Chemists are very fussy about details. HF is called hydrogen fluoride when it's in a solid form. It only becomes hydrofluoric acid if you put it in water so that it can pull apart and make those hydroniums. So in order for it to actually be called hydrofluoric acid, you need to have the little AQ sign beside it. That's very important. It seems like not a big deal. And you're right, sometimes chemists, they just kind of go fast and don't do that because they understand it's happening. But we should have good form when we're learning so we don't learn bad habits and we understand. But this means dissolved in water. So the AQ, aqueous, has to be there to make it hydrofluoric acid. Otherwise, it's just hydrogen fluoride. And it's a little lump of solid material sitting on the desk, and it doesn't do anything. Because the only way you can be an acid is if you go in the water and make hydronium ions. Okay? All right. You can also have, what's the next one down? Bromine, right? Hydrobromic acid, HBr. Hydrobromic acid. And we could have hydroiodic, HI. Hydroiodic. Hydroiodic, the OIO in there, right? Got to get that spelled right. Hydroiodic acid. And so on. We could go all the way down. Astatine, hydroastic, or astatic. Yeah, it would be hydroastatic acid, I guess. It's not very common. I've never actually even ever seen or used it, but I'm sure theoretically it could exist. But these are the common ones, and they're called binary acids because they're made of two things. You can see that. Binary means two. There's an H and an F, HCl, HBr, an H, and an I, right? And they're made like this. They all share one thing in common with their name. They all start with hydro. No other acids will start with hydro. Only these ones. Hydrofluoric, hydrochloric, hydrobromic, hydroiodic. And they all end with the ic. Okay? All right. The next kind of acids are acids that are formed with polyatomic ions. So let's call these polyatomic ions, or polyatomic acids, I guess we'll call it. Acids. Okay? So, what happens if we take a hydrogen and we join it with nitrate? HNO3. Remember nitrate. And we put our little AQ beside it. A little subscript. What do we call that? Well, it's not a binary acid, so we're not going to say hydro. We're just going to use the name of the polyatomic ion alone to name it. So it's just going to be, but we're going to call it ic though. So nitrate joined to hydrogen produces what's called nitric acid. But notice there's no hydro on it. It's just nitric acid. Nitric. And that comes from nitrate. Okay? So you should start to notice a pattern. Anything that ends with ate becomes an ic if it turns into an acid. Ate and ic go together. We could join hydrogen with sulfate, H2. It takes two hydrogens because sulfate is -2. And what do you think we would call that? Sulfuric acid. Sulfuric acid. So sulfate over here, hydrogen sulfate becomes sulfuric. 8 becomes ic. 8 becomes ic. Remember that. Next year in grade 11, you're going to learn about a whole bunch of other acids that have slightly different names, but they're all different patterns. I'm just going to introduce you to some of the most basic ones for now. Another common one is this one, H3PO4. With a little AQ, so we show that we dissolve it in water, so it can release those H's and make hydroniums, and of course this would be called phosphoric, from phosphate. That's the phosphate. Put it in water, and it will lose the H's, they will make hydroniums, and it will be called phosphoric acid. Another common one is H2CO3. Anybody want to guess what that one's called? Carbonate becomes carbonic. Carbonate becomes carbonic acid. Carbonic acid is often found in pop. Right? The acid of pop. In fact, if you take carbon dioxide and you put it into water, it will react with the water and it will produce carbonic acid. And that's one of the things that makes pop all bubbly and fizzy. And phosphoric acid is also found in pop. Believe it or not, we drink that stuff. But phosphoric acid can also be used to treat rust converters and things that you drip onto rusty metal to sort of remove the rust, or actually it changes the rust into a hard black chemical change, and that protects the metal from further rust. So rust treatments. So believe it or not, we drink it in our pop, but it's also a rust treatment. Cool how these chemicals are found in so many different things. And those are the most common. Oh, one more I guess we should do. Remember chlorate? HClO3, chlorate, and guess what? Any guesses? Chlorate would turn into Hydrochloric acid. Not hydrochloric. See, that's the difference. See? Chloric acid. Chloric acid is chlorate, ClO3, but hydrochloric acid is just a Cl. That's where it gets a little tricky. That's why we need to understand all the names. Hydrochloric and so on. Okay, so these are the acids that we have to sort of get into our memory. The ones that I've written here, the binary acids here, you have to know them. So you want to study this and sort of memorize them all. And then these polyatomic acids, nitric, sulfuric, phosphoric, carbonic, fluoric, and so on. These are the ones that I think we will be using the most often. So if you can memorize these 5, but you can make an acid with any polyatomic ion in a sense with hydrogen. Okay, so all of those polyatomics that we were learning about before could be used here, but we'll just focus on these for now because we want to get the idea of what goes on. Okay, so that's what an acid is and some of the ways that we name acids. Okay, now of course there are other common acids that we will hear about, but they have much more complicated chemical formulas. So they're not nice little simple easy formulas like this. Okay? Acetic acid, CH3COOH, right? That's something that that comes from the acetate. Remember acetate, the polyatomic acetate ion? It comes from there. That's acetic acid. But it's more complicated, right? That's vinegar. That's vinegar. And then we have other acids. I don't know the formula for them all off by heart because they're quite complicated, but citric acid would have a formula, you know, C6H12O something, and lots of different things like that. So the other acids that we encounter are a little more complex. But see this H right here? This is the H that can be popped off by water. Water can't really get at these H's because they're being held too tightly by the carbon. But water, because it's polar, can pull off this H, and that H can go on and become a hydronium. And so that's how vinegar becomes acidic as well. So that's how we name some of them. But it's more important, I guess, or equally important, to understand this little dance of water, the water dance. This, remember, is pure water. It just does this dance back and forth, back and forth. The molecules keep popping into two and then breaking up and popping together, and it's just a big jumble. But when you put an acid into the water, the acid also puts H's in there, which causes this H3O hydronium to sort of build up in excess and creates what we call an acidic solution. So I could mention, you could imagine that some chemicals will make a little bit of H3O that's extra, a little bit of extra hydronium, whereas other acids will make a lot of extra hydronium. Okay? If you look at these acids way down here, you'll notice that some of them have one H, some of them have two H's, and some of them have three. Right? So that means that when nitric acid gets put into water, it's going to give up one H plus to make hydroniums, to make H3Os. But look at sulfuric. There's two H's that can come off there at the front. Both of these can be released, and it can make two hydroniums for every one molecule of sulfuric acid. So that's like double, right? And look at phosphoric. It can make three. It can give 3 H pluses. Oops, not 31. 3 H pluses. Oh, I was pressing the wrong button. There we go. Right? So some molecules can give more than one, which would change how many there are. But again, it also depends on how easy it is for water to pull them off. And the problem with some of these acids is as soon as you pull off one, it becomes harder to pull the other two because they get stuck a little harder. And so we're going to learn later that some of these acids, even though they can donate lots of H's, they may not actually be that reactive. And we'll talk about concentrations, and we'll talk about the acid strength and things like that a little bit later. But I think we'll stop the video here. There's our introduction to what an acid is, the water dance, and what we call some of these acids.